one and all present here. It's my immense pleasure to welcome you all for today's talk series. Today's talk series is based on the topic Magnetic Nanomaterials by Dr. B. Gokul. He is working as assistant professor in Department of Physics at Kongunadu Arts and Science College, Coimbatore. He finished his master's and PhD in Kongunadu Arts and Science College, and he has 5 years of teaching experience and 10 years of experience in research. Council of Scientific and Industrial Research CSIR awarded him as a senior research fellowship, and Kongunadu Arts and Science College awarded him as Best Researcher Scholar Award for MPhil. His area of interest are permanent magnets for energy and sustainability application, materials modification through swift heavy ion irradiation, metal chalcogenic and oxide thin films for thermoelectric application. He also made 20 publications in international journals and 15 publications in national and international conferences. The floor is all yours, sir.
Uh,
Welcome you, sir.
Thank you. Uh, Thank you, Kalai. At this juncture, I thank Dr. Santosh and his team for having me. Good evening to one and all present here. Uh, so, my talk is today on magnetic nanomaterials. Myself is Dr. B. Gokul, Assistant Professor, Department of Physics, Kongunadu Arts and Science College, Coimbatore. So I have planned my talk on in this order, where we are going to see about brief history and origin of magnetism, permanent magnets for renewable energy applications, permanent magnets for memory device applications, and magnetic nanoparticles for medical applications, and I conclude my talk. So we are very well. We have played using magnets from childhood. We all have experienced the magnetic permanent magnets from childhood itself. Okay, to mankind, magnetism and magnets are known from 600 BC. The first magnetic material is iron oxide, which you call it as a magnetite. It is found in northern Greece near Magnesia. So Chinese have developed, used this magnet and developed a magnetic compass and have used for their navigation purpose. So magnets are used from 600 BC until now. Magnets play a very vital role in human life. So even in this COVID-19 situation, iron oxide nanoparticles are used to inhibit the growth of the COVID-19 virus. So in day-to-day life, without magnet, you cannot lead the day-to-day life. So magnets are most important and play a vital role in mankind. So whenever we think about magnet, two fundamental properties come to your mind. One is attraction and repulsion of the magnets. So how does these magnets or solids acquire this property? So to understand this, we want to we consider an atom. You know that atoms have a nucleus at its center and electrons revolve around it. So whenever an electron revolves or moves, it will exhibit to a magnetic field and electric field. Electric field is associated with the charge of the electron, whereas magnetic field is associated with the spin property of the electron. So magnet will have two basic properties, spin and charge. So the spin of the magnet is also can be classified into two types, upspin and downspin. So to have this attraction and repulsion, spin of the electron is responsible for the magnetism. So we can think all atoms have electrons, that is charge and spin in it. So we can call so all the elements in periodic table or all the elements in universe have the property of attraction and repulsion. So let's see it. So please look out this magnetic periodic table. This is a modern periodic table where it is classified on the basis of magnetic property. So all the elements in periodic table is classified into different magnetic properties. So, depending on the spin, magnets are classified as dia, para, ferro, antiferro, and ferrimagnetic. So, spin is responsible for magnetism, as we already seen. So, only the ferromagnetism will exhibit the property of attraction and repulsion. We can see why it is so. So when you consider a ferromagnetic material in its electronic structure at 3D orbital, it will have unpaired electron. For example, iron will have a 4 unpaired electron in its 3D orbital. So when you have a material with a paired electron, the magnetic field created by the one electron will be cancelled by the adjacent electron. This is because Pauli's exclusion principle restricts the two electrons who have a same spin. So a paired electron will have one upspin and one downspin. So you call it as an anti-parallelly aligned valence state. So you cannot exhibit it won't exhibit a magnetism. Whereas when you have a unpaired electron, it will exert a magnetic field. And so ferromagnetic exhibits this type of unpaired electron in its valence state. So it will exhibit a magnetic field where you feel the attraction and repulsion. Further, these magnetic moments or a magnetic spin are distributed as magnetic domains in the ferromagnetic materials. When you apply a magnetic field, external magnetic field, all these domains align parallel to the applied magnetic field. So it will have a strong attraction. When you have a unlike poles, it will have strong attraction. When you have like poles, you will have a strong repulsion. So to characterize the magnetic materials, so these ferromagnetic materials exhibit a very good hysteresis loop. So hysteresis loop is a characteristic phenomena, a characteristic property phenomena where ferromagnetic materials exhibit, where you can study about the remanence and coercivity and saturation magnetization of all these ferromagnets, which determines the characteristics of the permanent magnets or ferromagnets. So applications of magnetic field magnetism you concern everywhere we use the magnet like materials or magnetism. So permanent magnets, we have small iron oxide nanoparticles which are used in day-to-day life. It is predicted that each human using at least 5 magnets in their day-to-day life. So without magnet, we cannot realize or we cannot visualize the modern industry or modern life what we have, or sophisticated life what we have. Okay, so so what happens when so the above discussion is based on the bulk nature of the magnetic materials. So what happens when we reduce the size of the magnet to a nano scale? So when you consider a bulk magnet or bulk ferromagnet, it will have, as I already said, it will have ferromagnetic domains. So when you reduce, look at this diagram. I have the diagram is the graph is drawn between the coercivity and particle size. When you reduce the particle size of the magnetic material, the multi-domain particle will change into a single domain which have a critical size where the coercivity and the remanence of the magnetic materials are high, where you can use it for a strong magnetic applications. So it is very hard. Very hard magnets can be produced by reducing a magnetic particle size to a single domain. So further, we reduce the particle size of the ferromagnetic nanoparticles, and the ferromagnetic particle is changed into or converted into a superparamagnetic nanoparticle, where we don't have any coercivity or remnants. So in super paramagnetic region, you don't have any coercivity or remnants in the magnet. So it will give just a simple S type hysteresis loop, where you don't have a strong a big hysteresis loop. Okay. So what happens in the super paramagnetic region? So when particle size is reduced to below critical dimension, thermal energy dominates the magnetic anisotropic energy. So due to this, the spin of the magnetic materials fluctuates due to the temperature. So the magnetic spins are unstable. So you call it as a super paramagnetic nanoparticle, as a super paramagnetism. So when you magnet is in single domain, that is above critical dimension, you have a strong hysteresis loop, where you can have a large coercivity and high magnetic remnants. So both these have advantages in their domains. For example, single domain particles are promising candidates for permanent magnets in electrical vehicles, and you can use it for magnetic memory devices in hard disk and all. Whereas super paramagnetic nanoparticles are used in medical applications. So depending on hysteresis loop, you can classify it and you can use it for a different purposes. So we can see what are the scope of permanent magnets in renewable energy applications. So all say nowadays electrical vehicles are becoming a trendy in transportation, and windmills are used in renewable energy to have a current and all, to meet the electricity demand. So all these motors are used. Motors, permanent magnets are essential part and play a key role in it. So efficiency of these electrical vehicle motors and windmill motors are highly influenced by these permanent magnets. So depending on the hysteresis loop, and the permanent magnets are classified into two, as soft magnet and hard magnet. So quality of these permanent magnets are assessed by its remanence, residual magnetization, coercivity, and magnetic energy product, maximum energy product of the permanent magnet. When you have a high coercivity, remanence, and maximum energy product, you call it as a strong magnet and a quality magnet, where these properties or these parameters you can calculate from, or you can identify from the hysteresis loop. So already we have a few permanent magnets, that's quality permanent magnets in a market. And that is a niobium ferric bromide, samarium cobalt, aluminum nickel cobalt, and ferrite and magnets are already in the market. They have a high magnetic energy, or a maximum energy product up to 60 megagauss Oxide, which is whereas some NDFB and samarium cobalt are most widely used for energy applications. What we are talking about, we have already good quality magnets in the. So what is the need for new magnet? So as we see in this slide, these magnets are used in electrical vehicles, have a temperature instability. That is, electrical motors used in these electrical vehicles or have operating temperature above 200 degree or 300 degrees Celsius. So at this temperature, these permanent magnets or rare earth permanent magnets have a less maximum energy product, where its coercivity and magnetic resonances are not meeting up to the point. So the magnetic flux density given by these magnets not enough to drive the motor to have efficient electrical vehicles. So the electrical vehicles couldn't have a high mileage, or you cannot use these for practical applications. So further, you reduce these magnetic particles in nanoscale, its quality reduces due to superparamagnetism, so where you have unstable magnetic spin. So another major problem is diosporium content, where diosporium is used to increase this operating temperature. And the cost of diosporium is very high, and it is rarely abundant in Earth. So China is having the maximum diosporium in the world, and the cost of diosporium is also very high. So you cannot use it for practical applications in electrical vehicles. So you cannot reduce the cost of the electrical vehicles if you use a diosporium based niobium ferric bromide magnets. So we want to solve all these issues: instability, cost, and operating efficiency and all. To overcome this sort of problem, actually our requirement for efficient electrical devices, you need a maximum energy product magnet with the maximum energy product greater than 35 mega Gauss Orsted, which is which is exhibiting at 250 degrees Celsius and above, or and we want to have 300 to 400 degrees Celsius. So the first solution is proposed as exchange coupled magnet, where exchange coupled magnet will have two different phase magnets. One is hard and soft magnet. When these two magnets are made into contact, the exchange it is expected that exchange energy product, or maximum energy product increases to a level of application what we have. So different structures are practically proposed and utilized in the research. One of the important is or one of the successful uh, exchange coupled magnets are coaxial magnetic nanoparticles, where you can have a strong exchange coupling, and the magnetic maximum energy product has increased to the feasible level. Okay. So the another second solution is replacing the complete rare earth elements and using some elements without rare earth and earth abundant materials like iron, cobalt, nickel, and other. I have listed some of the rare earth free magnetic materials: magnesium, aluminum, zirconium, cobalt, hafnium, cobalt, magnesium, magnesium bismuth, hafnium oxide, zirconium, cobalt. So mostly they have cobalt, Mn, and bismuth, these type of particles, where you can use it in a nanostructured region, nanostructured size. You can have a large maximum energy product, so you can use it for a low cost electrical vehicles. So I have listed a few of the examples here. The first one is where the cerium, another low-cost rare earth material, is replaced with the high-cost diosporium in neodymium ferric bromide. So these are one of the results published in Advanced Functional Materials journal, where we see the coercivity, maximum energy product, and revenants have drastically increased, and depending on cerium concentration, all these have some variations also. So at nano dimension, they have a nano domains of size around 50 to 100 nanometer, exhibiting a maximum energy product up to 12 mega Gauss Orsted. This study have uh, given a promising way where diosporium can also be replaced by some low-cost rare earth materials, where you can use it for uh, uh, energy application. But these results are measured or measured in room temperature, but we need a high temperature uh, materials, operating materials to improve the quality of the permanent magnets. So another promising example is a exchange coupled hafnium ferric cobalt, iron cobalt nanocomposite. And basically, this is a nanomaterial, nanocomposite, where uh, this these materials are prepared using cluster deposition method. Cluster deposition method. The particle looks in a spherical shape of a size 13 nanometer, nearly 13 nanometer. So it is reduced to a very small size, uh, and you have beautiful structures around it where iron, cobalt, and hafnium have distributed over all the surfaces. Where I have shown the 10 images in color, so it is equally distributed and all over the surfaces of the all the complete nanoparticle. So it has achieved a maximum energy product up to 20.3 mg Orsted at room temperature. Okay, when it is measured at a high temperature up to 180 degrees Celsius, it can have 17 mg Orsted. So far, this this is one of the highest maximum energy product achieved now. So when you consider the structure of this permanent magnet, you have a hard magnetic phase of hafnium cobalt and soft magnet Fe cobalt. Okay, yeah, this hard magnet hafnium cobalt is embedded in the iron cobalt matrix and distributed over the matrix. So they couple with each other and increase the energy product of this magnet. So this is one of the best example, or which is a promising candidate for energy application. So what makes it better? Exchange couple, we have seen a few examples saying that exchange couple magnet can replace the already existing rare earth magnets. So what makes it better and a promising candidate and mechanism behind this? I have shown the left picture clearly shows the exchange couple magnet where soft magnetic, where a hard magnetic phase is embedded between uh, soft magnetic phase. When you look at the interface, uh, the hard magnet and the soft magnet have a parallel spin. So when we apply a magnetic field or an electrical field to this magnet, uh, the center of the soft magnet will have magnetic switching parallel to the aligned magnetic field. Whereas at the interface, hard magnetic spin couples the soft magnetic spin, so it won't allow to rotate it. So if you don't have any rotation, it pins the magnetic spin strongly to increase the coercivity of the magnetic materials. So ultimately, the coercivity and the remnants of these magnets will have a high value, and it increases when you have this exchange couple magnet. So one of the illustrations, as I have shown here, is MnBi and cobalt magnetic bilayers, where you can see at the center you have a straight center of the soft magnetic phase. You have a straight magnetic spins, where at the interface there is have a twinned or a torqued magnetic spin due to the coupling of MnBi hard magnet. So maximum energy product achieved by this magnet is 21.6 mg Orsted. This is also one of the promising result published in APS journal. As we have seen these examples are very high promising materials. But till date, we don't have any rare earth free permanent magnet to have a maximum energy product greater than 35 mg Orsted at temperature or above 250 degrees Celsius. The problem is alive, open for research. So many scopes are there to do some research in this area, where we can have use many magnetic materials coupled in the exchange coupling format or exchange coupling structure. So you can increase it when you increase it to 35 mg oxide, we can use it for electrical vehicles. So the cost and efficiency of these electrical vehicles will improve. So we can have a breakthrough through this research. So I open it for audience and other researchers to take this problem. So another important application or of the permanent magnets are memory devices. So we are using computers, and we are day by day the size of the computer is becoming smaller, and the processing speed is faster and faster, increasing faster and faster. I have given some a picture to see how computer the size of the computer is reduced in a period of time. So this is also show the reduction in magnetic memory devices. So we'll have now you are having a small pen drive where you can store hundreds of GB in a 1 inch area. So these magnetic devices also uses the permanent magnets for its magnetic storage. So you can see this is normally what we feel. So hard disk and CD drives, what we are using, can store the data for a long time, so roughly about 10 years. Whereas pen drive or flash devices, or flash drive devices, pen drives and small memory devices, what micro devices don't have a life greater than 3 to 5 years. Uh, the main problem is reduction in size. So reduction in size, reducing the limiting the lifetime of these memory devices. So in magnetic memory devices, we are using both hard and soft magnets. Where read head, right head, we are using soft magnet for reading head, or in a hard disk we have a hard magnet. Actually, what is the problem with these small memory devices is again the superparamagnetism. So, so nanomagnetic phenomena and GN magnetoresistance had increased the capacity of hard disk in thousandfold, and companies have ability to scale down these magnetic devices to nano regime. But superparamagnetic property of the nanomagnetic material is greater constraint, and it don't allow the reduction in size because of its thermal instability. So around 220, we have the diagram shows that at 100 GB per inch square, thermal stability of these magnetic layers are problem. So in memory devices, barium ferrite, cerium ferrite, iron oxide are the few are usually usual magnetic materials used in these memory devices. So earlier in 2010 and or 100 GB per inch square is the target of the uh, companies to achieve the maximum storage. So, what is the problem with the superparamagnetism? How it's affecting memory devices? So, as far as memory devices concerned, memory devices have two, two magnetic ferromagnetic layers separated by a non-magnetic layer between. So, it is a three-layer device. And so when the when the spin of the magnetic layers are anti-parallel, magnetic memory device will feel a high resistance where you can store a bit zero. So you know that computer store a bit when 0 and 1. So when it's high resistance, due to anti-parallel spin, you can store a bit zero. When you have a parallel spin between the two magnetic layers, where you can store a bit 1. So uh, this is the normal structure of the ferromagnetic layers or a magnetic memory device in the what we are using hard disk and so. So when I try to store a bit 0 or 1, by reducing the size of these magnetic layers, the magnetic spin flip. So when I try to store a 0, it flips and store the magnetic bit 1. So I cannot store the desired bit in the memory device due to this superparamagnetic property. So by it hinders the reduction in size of the size and areal density of the magnetic memory devices. So it is a major hindrance for the companies to have a efficient and small sized magnetic memory devices. To overcome this problem, people have come up with the idea of exchange bias coupling effect. To have this exchange bias coupling effect, a ferromagnetic layer and an antiferromagnetic layer are made into contact. So antiferromagnetic layer will have an anti-parallel alignment. So you cannot disturb it with a normal magnetic field or a room temperature or the normal temperature effect will not affect the antiferromagnetic spins at the and it will have a strong anisotropic energy. When these two magnetic, ferromagnetic and antiferromagnetic, are made in contact, and when you apply a magnetic field or a current, and when you current, the at the interface, the ferromagnetic spin will be coupled by the strong antiferromagnet. So as we see the ferromagnetic layers at nanoscale, it will have only superparamagnetic properties. So it will have a flipped or a fluctuating spin. When you made a contact with the antiferromagnetic layer, it will pin the flipping spin and increase the stability of the magnetic memory devices. So I can store a bit 0 or 1, or I can store a bit 0 and 1, what I want to where I desire I can store. So this magnetic effect you can observe through a shift in the magnetic hysteresis loop from its symmetry point. So you can see it in animation where the magnetic hysteresis loop shift towards the left. That is a negative exchange bias coupling usually observed in the magnetic memory devices, where you can also have a positive exchange bias effect, a vertical shift. So many types of structures are used. So depending on it, the magnetic shift will be accounted or seen. So when you have a shift in the magnetic hysteresis loop, you can say that you have a strong magnetic device where you can store a large amount of data and all. So this is the major or a basic phenomena used in many magnetic memory devices, and even in future also you cannot avoid this exchange bias effect um, by exchange bias effect um, um, and play a key role in it. So I have given some overview. One of the promising uh, magnetic memory device is spin wall device, where it is used in a read to read the magnetic storage stored data. We use a spin wall device. So spin wall devices ultimately have used by found by Professor Stuart Parkin, a British physicist. So he pioneered the spin wall device by using this exchange bias effect, so which is responsible for a terabyte storage. Now we are using terabyte hard disk. So by this spin wall device only, we have achieved this type of terabyte storage capacity. So the basic phenomena behind this, the same exchange bias coupling effect. So nanostructures have allowed us to have uh, different types of nanocomposites like core cell, different types of embedded structures in exchange bias phenomena. So this diagram illustrates a different magnetic materials like antiferromagnetic coupling, for spin glass ferromagnetic coupling, that is SG, spin glass ferromagnetic coupling, and ferrimagnet antiferromagnetic coupling in different nanostructures like core cell, thin film, embedded nanostructures, and all. So with this different nanostructures, some people have achieved uh, uh, room temperature exchange bias effect, which is most important to types of nanostructures where exchange bias coupling is realized. So different structures have their own advantage and disadvantage, but the most promising structure to realize a very good exchange bias effect and promising magnetic memory devices, core cell nanoparticles. So nowadays people are trying to prepare different types of core cell nanoparticles, and where we can use it for memory devices in future. So I have given some choice of materials where the condition to choose this choice is both ferromagnetic material and antiferromagnetic material should have the Curie temperature and Néel temperature above the room temperature. What is the ambient temperature? And then the second condition, the ferromagnetic Curie temperature should be higher than the antiferromagnetic Néel temperature. So with this condition, I have chosen some given the some choice of ferromagnetic and antiferromagnetic materials. People are in literature, I can see room temperature ferromagnetism is achieved by using these materials, where iridium Mn and cobalt ferrite or cobalt FEP, Fe platinum structures have a good exchange bias coupling. Already they have they are used in the commercial purpose also. Well, the rest of the are promising, but they are in research purpose. They have some disadvantages. Whereas Fe platinum and iridium Mn magnetic particles or magnetic layers are already used in magnetic hard disks and read heads also. So, one of the major advantage of this exchange bias effect is seen in this heat assisted magnetic recording and microwave assisted magnetic recording, and this is also have this exchange bias in layers. And Western digital company have come up with these two magnetic storage devices which can store up to 40 terabyte in a inch, in an inch square area, where you can store a 40 terabyte inch. So people have are you this Western digital company have trying to market in very near future. I will put some video, a small video. Please, you can see. So this is what a normal magnetic hard device is used, where the areal density is very high. When you reduce the areal density of this magnetic read head, it will have a thermal stability problem. So people have come up with this heat-assisted magnetic recording and microwave magnetic recording, but it is replaced by a small laser. It will have it will uh, go through the magnetic layer, and it will record, it will manipulate the magnetic spins, and you can be used to store the data. When it is heat assisted magnetic layer, we use a laser which is which will always harm the magnetic layer and disturbs the storage devices. um, this Western digital company come up with a new idea, having a microwave device using spin torque oscillator, where it uses a low temperature and uses a megahertz frequency or gigahertz frequency energy, and it stored the magnetic spin without disturbing or harming the layer on the surface of the magnetic hard devices. So this technology is going to come in the market in near future, having 40 terabyte per inch square. So you can have a hard disk of 40 terabyte in your normal computer itself in a near 2025 or 2023. So this so microwave assisted magnetic storage device is also composed of the exchange bias coupling layers, what we have already seen on, as we seen in the normal magnetic hard disk. So, but the only difference is it will have a circular discs where The spin of the magnetic layers will have a circular structure. So it will have a chiral magnetic spin. When you apply an electric field across these across the junctions, uh, at the center of this chiral, we call it as a vertex. At the center of the vertex, the parallel magnetic spin will switch and become a perpendicular. So at the circumference of the magnetic disk, you will have a circular parallel magnetic spins parallel to the thin layers, whereas at the center you have a perpendicular magnetic field. So when you apply a current, you can switch the magnetic spin perpendicular and parallel, where you can store a bit zero using a perpendicular magnetic spin, where you can store bits one using a parallel spin. So this when it is switching the magnetic spin to a perpendicular direction, it will emit a strong frequency in terms of megahertz and gigahertz. So this microwave frequency is used to store the data 0 and 1. So you call it as a spin torque oscillator, where you don't need to have a laser and other structure distorting magnetic devices in a magnetic hard disk. So this spin torque oscillator utilized by microwave assisted magnetic recording device be a will be a very good promising candidate for high storage magnetic devices. So another thing in research is racetrack memory devices, which is based on nanowires. Surprisingly, this magnet devices uses copper as their material, where copper is also having some unpaired electron in its 3D orbital. If you see, one unpaired electron will be there for. So utilizing this one unpaired electron, you can store you can store enormous data. So if we look at this, copper nanovirus embedded in U structure, where the moving layers, you call it as magnetic domains. So by moving the magnetic domains, you can store data, write a data by applying a positive current pulse. When you apply a positive current pulse, you can move the magnetic domains and you can store the magnetic data. And when you apply a negative current pulse opposite to the positive current pulse, where you can read the data, you can rub it, you can again you can write it in a nanosecond scale or in a very microsecond. So you can read and write the data, erase, copy, and everything in a very few microseconds. So you can transfer data in GB and terabyte in a very short time without losing any data. So we are using magnetic nanowires. The areal density also is reduced. So this racetrack memory device is also invented by Professor Stuart Parkin in IBM laboratory, but these devices are still in laboratory level. So many phenomenon is understandable. And the domain wall motion, controlling domain wall motion is a very critical task in this magnetic memory device. But sure, in near future, in 2050, we'll have a racetrack memory devices where you can store hundreds and thousands of terabyte in area what you have in a hard disk. So with this thing, I switch my talk to magnetic nanoparticles in applications of medical application. Uh, so as far as medical application is concerned, you have it is a vast area. Magnetic nanoparticles are used in cancer therapy, drug delivery, medical imaging, and it is used as a MRI contrast reagent, gene therapy, gene coding, and all of that. It's a vast area, but I have restricted myself to a very particular thing. So this slide illustrates you the inox and nanoparticle structure. where most of the medical applications of iron oxide nanoparticle is only used. So you can have you can prepare it in a simple laboratory conditions. In the left hand side of you, so some of the methods: co-precipitation, thermal decomposition, salt gel, and micro emulsion method. Using simple beakers, you can prepare it, and you can have achieve a different shapes of iron oxide nanoparticles, and with the uniform size distribution, and also maintaining the superparamagnetism, because superparamagnetism is essential for medical applications. If you have a remnants and a cohesivity, uh, you cannot guide the magnetic particle in your body, and so it will harm the tissues and all. Superparamagnetism is essential for medical applications. But iron oxide is, I think, iron oxide is only nanoparticle can have this much superparamagnetic effect, and people are using this in medical and preclinical level also. So I restrict myself to very particularly about magnetic particle imaging. And there are different applications also, like MRI and cancer therapy, magnetic hyperthermia and all. So, but very few talks about magnetic particle imaging. So I have chosen this. So this magnetic particle imaging also uses iron oxide nanoparticles, super paramagnetic iron oxide nanoparticles uh, with a spherical or and cubical size. Uh, so, how this magnetic particle imaging works, or how it records the tissue, and how it is used. So, first, the magnetic nanoparticle, that is iron oxide nanoparticle, is injected into the body. Okay, when it is injected, and magnetic external magnetic field is used, and guided guide these magnetic particles to attach with a tumor, or area in a body, in which area we want to scan or want to image. The external magnetic field is given and has been chosen and to guide these magnetic nanoparticles. So if after getting on the tissue what we want to image, alternating magnetic field is applied externally. When you apply an external alternating magnetic field, due to superparamagnetism, the magnetic spin flips or rotates due to this alternating magnetic externally applied field. So it exhibits a magnetic induction when you put a coil on it. So it will induce a varying magnetic induction, which is given in the graph. So it will vary according to the time. It vary according to the time. So when so these magnetic particles, when reaches this when induces this alternating magnetic induction, next step is you want to find the field free point in the in the magnetic field. Field free point is nothing but a point where you don't have any field or magnetic field. So I have in this diagram FFP. I have mentioned FFP. At the center of the magnetic lines of force, you have a nullify point where you call it as a field free point. So with this field, if you find this field free point by using by capturing that signal, you call it as a non-linear magnetic response. The signal is non-linearly varying. So at this nullify point, you get a varying magnetic field, but it is non-linear. So use Fourier transform to maximize this signal. So by guiding this nullify point, you can scan all through the body, and you can identify the cancer tissues and all. Whereas when these nullify point is not utilized, you have a saturation magnetic region, or where you don't have a magnetic induction. So the signal is very low, so you cannot image any tissue. So we want to first to find the field free point where it will give a strong signal of a non-linear magnetic response, so you can image correspondingly the cancer tissues and all. So what is the uniqueness of this magnetic particle imaging is, and over magnetic resonance imaging and optical imaging is, it is a highly spatially resolution. It can give signal only from the magnetic nanoparticles. So if you identify the tissue and when you couple the tissue and when you attach the tissue and the magnetic particle, you can have a very good image, and you can see the image, or you can capture the image very faster in very few nanoseconds, or very few microseconds. So whereas in MRI and other optical CT scans or other scans what we have, it will give us signals from protons, and other resonance signals are received where where you cannot have a high spatial resolution. So it will distort, it will give it don't give a clear image about the tissues and cancer and all. So this magnetic particle imaging is still in a preclinical research. Bruker and Phillips company have are doing research to increase the quality, to increase the quality image of this magnetic particle image. So in very near future, magnetic nanoparticle image will be in hospitals to have a high uh, to find the high tissue affected tissues in a very precise manner. So, so with this, I conclude my talk, where magnets are essential. So in day-to-day life, where we are using in electrical vehicles, watches, switches, cell phones, and in memory devices, and also in medical application, and also various. So thought is magnets are essential, and it plays a very vital role in human life. So, so I conclude this talk, and then I like to acknowledge my team. First of all, I acknowledge my college management, Honorable Secretary Dr. C. Vasgi, ma'am, for giving this excellent platform and laboratory to do my research. And I thank my research supervisor, Dr. R. Satyamurthy. He's backbone of my all research ideas, and I thank him for his encouragement, continuous encouragement. And also, I thank Dr. P. Saravanan, DMRL Hyderabad, and Dr. Ashokan from IUAC, New Delhi, and Dr. P. Madheshwaran of Kongunadu Arts and Science College. These three people have played a vital role in my own research. So what I have and what I am doing now is due to all these people. And also, I thank all my group members, past group members of my Kongunadu Arts and Science College. So I also thank all for their patient listening. So if you have any questions, you can ask.
Um, Hello.
Yeah, yeah, go ahead, please.
Yeah. Santosh sir, can we ask questions now?
Yeah, ask it, sir.
Okay. Yeah. First of all, good evening, sir. My name is Hariharan, and thank you so much for such a wonderful lecture.
Thank you.
I was actually working with magnetic nanoparticles for targeted drug delivery application,
Yeah.
and
Yes, sir.
I also worked with superparamagnetic nanoparticles. So I was eagerly looking forward for this lecture,
Thank
and I
you.
learned a
Thank
lot
you.
about HLSS loop and all.
Mm.
It was very nice. But sir,
Thank you.
I had few doubts.
Yeah,
Number one
please.
is that you had spoken about laser, right?
Laser, yeah.
Laser for magnetic recording.
Yes.
So what type of a laser are you using, and what is the frequency?
So actually, it is a semiconductor diode laser. Semiconductor diode laser. So
Okay.
the frequency is around some few hundred megahertz or gigahertz frequency.
Okay.
But the problem is it will damage. Now we are also having the laser in our CD disk writing also. It will
Okay.
harm the
Yeah,
layers of
that's
the
what.
magnet.
Yeah, that's what even I had a doubt that will that
So
memory
it
not
will
be volatile?
it is a it is a it will damage the magnetic layers, but that's why we are going for a microwave devices, spin
Micro
torque
devices. Yeah.
oscillator and all. So
Okay.
with the because it will having, in the video also I have shown that 400 to 700 degrees Celsius it will emit.
Yeah.
So
Yeah.
in that point we'll lose all the magnetism
Right.
of the magnetic layers. It will harm the so but we have what we have is they don't have that temperature. No, now what
Right.
we are using in hard sun, we don't have such temperature. We use only to 70 to 80 100 degrees Celsius, so it won't harm these devices. But when you increase the aerial density, you
Hmm.
want such a high strong laser to have that aerial density capacity, but it will affect the layer. So only people come up with microwave devices
Right.
like spin torque
Right.
oscillator and
Right. And one more question is, sir, that you talked about the coupled coagulated method, right? Wherein you are using some coagulated technique, synthesis technique to
yeah,
prepare.
uh, what
Uh,
for ion oxide nanoparticles or what you
no,
are
no, no,
asking?
no. The during the beginning of the slides, you talked about a method of synthesis,
Yeah, cluster
wherein
deposition method, I think.
cluster deposition method, right?
Yeah. Okay.
Right. So
Uh,
yeah, sorry, cluster deposition, right? So in cluster deposition method, sir, normally what the problem we are facing in
yeah.
nanotechnology is that when you apply a magnetic field and when you apply like nanoparticles as a cluster,
Yeah.
when you put it in our body, they tend to agglomerate very easily.
So the thing is, that thing is only for permanent magnets. You cannot use it for a medical application.
Yeah, for medical application, then sir, what do you suggest? Like how should we?
My suggestion is this type of synthesis methods. You can use it for many applications. It's a simple colloidal synthesis method is enough. People are using it. Even when I'm talking about magnetic particle imaging, the
Hmm?
inventor is used just water using the solvent water. They use it in magnetic particle imaging. So simple colloidal synthesis method is enough to have a mono-sized different shapes of nanoparticles of ion oxide nanoparticles. But what I'm cluster deposition method is only used for a permanent magnets for electrical vehicle applications and a magnetic
Okay,
recording device. You cannot use it for I mean, it is a thin
okay.
film form, I think.
Permanent magnets, right, right. All right.
Yeah,
Okay, not for, yeah, not for medical. Yeah, right.
not
That's
for
what I was
medical
asking.
application. You cannot use it for medical applications.
Yeah, actually, like mine was focused on medical applications, so I wanted to learn more about that. Like,
Oh, thank you,
so
thank you.
yeah. And sir, like, what is the reason except for say contamination? What can be the reason that we lose magnetism in the hysteresis loop, where you don't get a proper hysteresis loop, even if your material is a super paramagnetic material?
So actually, the instability of the spin is reason for superparamagnetism. Okay,
Okay.
uh, when you think about a ferromagnetic hysteresis loop, uh,
Yeah.
when you apply a magnetic field in a ferromagnetic material,
Yeah.
the initial curve will grow and come to saturation point. Okay,
Yes.
saturation
Yes.
point of magnetism, and you reverse the magnetic field. uh,
Yes.
in permanent magnet, not all the magnetic spin is reversed and obey the initial curve. So it will
Mm,
have
mm.
a remnants and coercivity, obviously.
Yes.
But where in
Mm.
case of superparamagnetic material, it follows the when you reverse the magnetic field, all the spin will get reversed according to the magnetic field and will follow the initial curve. So
Right.
obviously we have a zero magnetism, sorry, zero magnetic coercivity and remnants
Right.
for medical applications. So if you have a
Right.
remnants and coercivity, you cannot guide the magnetic particle inside your body. So
Right.
magnetic
Right.
particle
Right.
will remain some other where in your body, and you will lose the efficiency of magnetic imaging and all.
Right. Right. Right.
So
Right.
that is a
Right.
problem with magnetic particle imaging, really. So
Right.
you want a well dispersed ion oxide nanoparticles in water
Mm,
or any other biocompatible solvent. Even
mm,
it is very compatible in a blood, or when you inject it in inside your body or inside your
mm,
vein, it should be
mm.
compatible to your body
Oh yeah.
also. So you want to
Yeah. Yeah.
accordingly want to choose the some ligands to disperse the ion oxide nanoparticles.
Yeah. No, sir. What my question was that
Okay.
sorry for the background noise.
Oh,
Uh,
no problem.
what my question was that if sometimes I have noticed that I get a big curve for when I take VSM graphs, I get a
Okay.
big curve sometime, not
Okay.
the curve
Okay.
which is expected for the super paramagnetic materials.
Okay.
So
So
what is the reason for that?
the actual reason is your particle don't have a uniform size distribution. For
Okay.
example, when we talk about the size of the nanoparticle, for
Yeah.
example, ion oxide nanoparticle, so above 30 nanometer, the
Mm.
ion oxide nanoparticle will have a ferromagnetic property.
Yeah.
Okay, so below 30
Okay.
nanometer, it is a superparamagnetic particle.
Yes.
So
Okay. Below
if
30.
you
Yeah.
if you result in some big hysteresis loop with a gap in between it,
Mm.
this is due to
Okay.
ferromagnetism,
Paramagnetic.
where it is exhibited by the nanoparticle size of
About
above
30.
30 nanometer.
About
Okay,
30.
so
Okay.
you wanted to restrict the particle size below 30 nanometer, so you can have it, and you want to have and you want to have size distribution, a uniform size distribution also. Otherwise, you will
Right.
get this ferromagnetic loop where it will be a problem for medical applications.
Right. Right. Okay. Okay. Thank you so much, sir. Thank you. It was very
Thank you
nice
very much.
listening to your lecture. Thank you.
Thank you.
Any queries? So thank you for Kalai. Kalai Kalanjiam.
So, yes,
Yeah,
sir.
just wind
Thank
up.
you for patiently listening.
Thank you, sir. Thank you so much for your session. Very nice session, sir.
Thank
Thank
you.
you.
Thank you.
Kalai Kalanjiam, wind up the session.
Okay, sir. Thank you, sir, for your mesmerizing speech. Tomorrow's talk is on the topic an overview of thin film modification by Dr. P. Madheshwaran. Thank you all.